I think you're really going to like 4.2. 4.2 is basic differentiation rules. It's the introduction to these basically shortcuts of deriving. So in 4.1, the previous section, what I had you do was use the limit approach, also known probably as the long way of calculating these slopes of the tangent lines. And what I hoped through that long way or through that limit approach is that you really saw the definition of a derivative and what it was doing. We were looking at secant lines, which would have two different points with a change in x between the two different points. So from here, this x has a certain delta x to get certain change in x to get to this x value. So what we were looking at was the limit approach took that change in the x and it started to make it smaller and smaller until there was essentially no change in x. So you had a point right on top of the point. And that is what we would call a tangent line. It's a line that passes one point on a curve. Hopefully that long way helped you establish that. Now we're going to be looking at shortcuts to quickly derive functions. We're going to be throwing these words around pretty frequently. So derivative is that instantaneous rate of change. It's the slope of the tangent lines. Differentiation is the process. So if I say through differentiation, find the slope of the tangent line, that's just the process you're going to be using. There's various differentiation processes, such as the limit approach. Derive, that is the act of finding. So you guys are going to be deriving and looking for derivatives. And then differentiate, to differentiate is also a verb just like derive. And differentiable, that would describe a function as being able to be derived. And this is a beautiful slide of differentiation. These are all the process that I used in order to find these derivatives. And what I hope is that you can kind of establish a certain pattern that's happening or a certain relationship from here to here or here to here. And I know a lot of you started to see that pattern with all the problems that you did. So now here are those shortcuts and hopefully those patterns that you picked out. So all this is saying, remember this is our notation for deriving. If you are going to be deriving a certain function that happens to be a power with respect to x, so your x and your x line up, you're deriving with respect to x. What you're going to be doing then is taking the exponent of that power down as a multiplier and then reducing that power by 1. So here would be an example. What you could go ahead and do then is you can say the derivative of that is going to be take that 4 down as a multiplier, x, and then reduce our power by 1, so it's going to be 3. Okay. Understand if I asked you to do this the long way using that limit approach, it would be a bit tedious because you would have to take that x plus delta x to the 4th minus x squared, and this would require a lot of FOILing. Okay, so let's look at another one. Let's look at like the power x to the 1st, okay, or just x. So keep in mind you could drop down that exponent and then you're going to reduce this by 1. It's going to become x to the 0. So basically that just became 1. Okay, so looking back at our previous slide, you can see how that happened. For this one, for example, you would bring down that power of 1. 1 times 4 would just be that 4, and then we would get x to the 0. Here would have been our 2 brought down. There's that 2, that original exponent, and this was reduced by 1. And you can see that going on in a couple of these other ones. All right, the constant rule. Let's look at something like this. If I asked you to derive, for example, 1's a constant, this is always just going to be equal to 0. Any constants are going to just basically drop out. And the reason being is if we looked at the function, let's look at this function y equals 1. What does that function originally look like? Well, it's a horizontal line at all y values being 1. So it's going to look something like this. If I asked you what is the slope of this linear equation, what is the rate of change? That's what I'm asking for here, right? The rate of change, the instantaneous rate of change. Well, the instantaneous rate of change at every single one of these points is always going to be 0. The rate of change is 0. Slope is 0. All right, here's some more rules. There's the constant rule. Let's say I had something like 4x to the 2nd, okay, and I wanted to derive that. What you can go ahead and do is pull that 4 out of there. 4 d dx of x squared. And so now what you're saying is you had this constant and this function with respect to x here, and what you can do is pull that out and then just derive with respect to x. So here now we're deriving with respect to x. You would get 4 times, bring down that 2, x to the, reduce it by 1, so now we would have 8x. Alright, sum and difference rule, that's just if you have multiple x terms going on. So if you had x squared plus, let's say, 2x, and I wanted to derive that, how you could possibly look at this is just take the derivative of this first function with respect to x, or in terms of x, and let's go ahead and take the derivative of that in terms of x, and you could just appropriately use, now what we have is the power rule. Okay, and we can also appropriately use the constant rule, and so it would be 2 times, what's the derivative of just x? Well, that's going to be, if you need to do it off to the side here, bring down that 1, we would have 1 times x to the 0, so basically that's just 2 times x plus 2. Okay, so you can see that drop down, basically this dropped out. Alright, same thing if you had subtraction. Had this been subtraction, then you could go ahead and subtract all of these. Rewrites may be required. So in order to remove any denominators, we don't have any rules for something like this. If I had 1 over x to the 5th, we don't have any rules of division yet. Okay, so you can't just, I'm going to repeat this, you cannot just derive the top and then derive the bottom. It is not, there is no rule for that. I'm going to repeat that again. You can't just go ahead and then derive with respect to x the top and derive with respect to x the bottom. Okay, this is bad. We have no rule that states you can do that. So rewrites might be required. So instead of having this be a fraction like that, I'm going to cross the line, change the sign. This is going to become x to the -5th. Okay, no big deal then, because now, just like we were saying, we can now use this as a power with an exponent. So you can go ahead and say, to derive this, f, or find f prime of x, I'm going to go ahead and derive this side here. And now that it's a power, you can go ahead and just state, bring down that -5, x, and then -5 minus 1. This whole thing is going to be -5 x to the -6. There we go. And if you want to rewrite that, now you can take your -5, that stays the same, but now your power, this thing right here, can cross the line, change the sign back, and this is what you have. Right? To remove roots, so let's say that I had f of x is equal to cubed root, so let's say cube root of x. So have no rules, right? Have no rules so far that I just presented in those last two slides that have any kind of roots. But remember that any kind of root can be written as rational exponents. So instead of having the cube root written like that, I'm going to have x to the 1/3. Okay, so now same thing applies. If I wanted to find the derivative with respect to x of this function that has x in it, then I can go ahead and say, use the power rule. Okay, so this is just going to be 1/3 comes down, my exponent comes down, and you might have to do a little bit of fraction work here. I need a common denominator, so there's my common denominator. And I'm going to subtract these. What I'm going to get is 1/3 times x to the -2/3. And if you want to, you can rewrite this. So keep in mind this is technically 1/3 times x to the -2/3 over x. So you could write this as, this is going to cross the line, change the sign. We have 1/3 times, and then x to the 2/3. Now don't forget, your fraction, your denominator of a exponent that's a fraction, that's the root, and this is actually the power. So overall, you could write it like this. 1/3 times the cubed root of x squared. Okay? Kind of interesting, but that's how you could do it. So I am going to do number 1a with you, which gives you y equals x to the 1/2. And it says, find the slope of the tangent line to this power at the point 1, 1. So I need to find the slope of the tangent, also known as the derivative. Same thing, right? I could have asked for the derivative. Your book asks in this case for the slope of the tangent. So all I need to do is derive this. One way to notate a derivative, y prime, is the way of notating that I want to derive this y. And also then, what is this y written with respect to? Well, it's x, where we've written y in terms of some sort of x expression. So I am deriving with respect to x. So we have x to the 1/2. And then, so y prime is equal to, by the power rule, I can go ahead and bring down that 1/2 times x to the 1/2 minus 1. So y prime is equal to 1/2, and then I need a common denominator, so I'm going to multiply top and bottom of that one by 2. So then this is going to be x to the negative 1/2. I could rewrite this. Y prime is equal to, cross the line, change the sign of my exponent. I have 1 over 2 times x to the 1/2, and so that can be written y prime equals 1 over 2 times the square root of x. Okay, so now here's the thing where I want to find what is the derivative at this point. We're only interested in plugging in the 1, because if you were to graph this function, remember parent function, this is just y equals the square root of x. So parent function would have looked something like this, over 4 up 2, because the square root of 4 is 2. Whoops. Okay, so I missed my mark there. Okay. If we were to ask you, or if I were to ask you, what is the tangent line that's going through this point right here, that 1, 1? So keep in mind that this right here is the equation or the function that will give you the derivative or the slope of the tangent at any given point on this graph. So all you need to do is say that I'm interested in the point where x is equal to 1. What is that tangent line equal to? So y prime, I'm going to plug in my x value, 1. What I get is this is equal to 1/2. Okay, so y prime, another way to say it, f prime of 1 is equal to 1/2. Okay, so my derivative at x equals 1 on my function is going to be 1/2. You also are given problems like this. I'm going to do number 21. Y equals 5 over 2x to the second. And it says rewrite, differentiate, and simplify. So I'm going to first rewrite. So careful with your rewrite, because all you're trying to do is you're trying to get this right here. This is my power. It's a base and an exponent. I'm going to cross a line, change the sign. So I'm going to rewrite this as y equals 5 over 2, and then I'm going to cross that line, change the sign to be x to the negative 2. Okay, I haven't differentiated at all yet. I have not gone through the process of driving at all. So another way to write this too would be 5/2 times x to the negative 2, right? So now I'm going to differentiate, or I'm going to derive. So I'm going to just go ahead, automatically pull that 5/2 up to the front, x to the negative 2. Okay, so I use the idea that this is a scalar multiple. Okay, I'm going to pull that multiple outside, and then I'm going to just seek this out as a power and use the power rule. So y prime is equal to 5/2, and then now here is where I'm going to take this chunk and differentiate. So we have x to the second, negative second, so pull down that negative 2, times x, and I'm going to subtract 1 off of that. We're going to get negative 3. Okay, so now it says to now simplify. So y prime is equal to, we have 5 over 2 times negative 2. I'm going to write this as negative 2 over 1 times, and now here's the thing. They do want positive powers, so here is everything just kind of piece by piece written out as factors. I'm going to simplify this all. So these cancel each other out. 2 divided by 2 is 1. Negative 2 divided by 2 is negative 1. Cross the line, change the sign. So I have 5 times negative 1, which is negative 5, over 1, times, cross the line, change the sign. There's technically a 1 here, but this is the power that's going to be crossing the line. We have 1 over x to the third. So all in all, you get negative 5 over x to the third. Done. Okay, simplified. One thing that I do want to just bring up, okay, and I had this last year, is the projectile motion function. The projectile motion function is when you toss something straight up in the air and you let it fall. So let's look at a problem like this. Stephen throws a ball up from his waist level at 1 meter above the ground. He throws it at the speed of 18 meters per second and means to catch it, but he misses and it falls to the ground. So let's model this. When I say model this, you could represent it in a graph. You could represent it as an equation. So the projectile motion function is merely a quadratic. So remember that from last year. Quadratic, I mean, basically, if you thought of what something being thrown up in the air and falling down, it's going to look like that, and that's our parabola. So this is what we're going to be using, but we'll know that always the acceleration of gravity is negative 9.8. The acceleration meters per second squared, and in feet it's negative 32 feet per second squared. So keep in mind that that's always going to be constant. Acceleration of gravity never changes, otherwise we'd be waking up to pretty interesting lives where, I mean, the force on us is always changing. But it's not, luckily, so we're just dealing with that. Initial velocity, you're going to get that from your problem. Initial height, you're going to get that from your problem. As soon as you know these three factors, you can calculate the exact height and position or displacement of that ball over a certain period of time. So you get height out of this equation. So let's just demonstrate what's going on. At t equals 0, he just has that ball at height of 1. That was that 1 meter above the ground, and I am doing it in meters. Okay, so after 0.9 seconds, it's going to be at 13.2, because what you could be doing, first of all, if you went back to this equation, I should fill these in. B is going to be 18, C is going to be 1. So if you, sorry. No, bad. Use this one. Okay, so we're going to use this because it's in meters. Go back up to the problem, we're all in meters. So this is going to be 18 and this is going to be 1. Use this equation if you want to and check my chart. So this is going to be my chart. So after 0.9 seconds have passed, that ball is going to be at 13.2 meters in the air. Okay, Stephen's freaking out down there. I showed this in your pre-calc class last year. So that's what it looks like. Put this on your calculator, in your graphing calculators. How fun is that? And you're going to get that in your graphing calculator. Otherwise, this is just me kind of tracking that height of the ball. So it's as we're moving across our time, also the heights are changing. So just keep that in mind. The reason why we have this is just to keep those in mind, because after you establish this 16x squared plus 18x plus 1, and you have this function, and if I were to ask what's the instantaneous velocity, so what we would be able to do is, if I wanted you to find the instantaneous rate of change, you would know you would have to drive it. So here's my notation for that. I'm going to go ahead and notate it on this side. So we have negative 16x squared plus 18x plus 1. And then you can use all the properties that we just described. So I can take these piece by piece at a time. Negative 16x squared plus d dx of 18x plus d dx of 1. So know right there that that was using the sum and difference property. And then I could also take these constants out to the front. So sorry, I'm going to have to write over here. We have negative 16d dx x squared plus 18d dx of x plus d, and this is just a constant, so I'm going to leave that. So now this would be negative 16 times 2x to the first, because I'm going to use the power rule, plus 18 times, I'm also going to use the power rule here, but what you're going to start to get used to is that an x is just going to become 1, because you would have that 1, drop that down, x to the 0 would be 1, so 18 times 1 plus 0. So our h prime of t is equal to negative 32x plus 18, and this would give you the instantaneous velocity at any given point. So if I wanted to find out at time equals 1, 2, 3, at time equals about 3, what his velocity or rate of change was at that very moment, you can just plug in the 3 into this formula or this derivative function and you would get that. Here is your problems. Good luck with those. May the speed of the shortcuts be with you.